Many students encounter SO10 through tables filled with mysterious numbers 10, 16, 45, 120, 126, and many others. These numbers often appear in discussions of grand unified theories, GUTs, but at first they can feel like isolated facts that simply need to be memorized. Why does 16 contain one generation of fermions? Why do gauge bosons live in 45? Why does 120 suddenly appear in products like 16 times 16? The purpose of this guide is to show that these numbers are not random. They belong to a surprisingly organized structure. To understand this structure, it helps to recall a small amount of Lie theory. A Lie group has an associated Lie algebra. Inside the Lie algebra, one chooses a Cartan subalgebra, and its eigenvalues organize the theory into roots and weights. The root system determines the Dynkin diagram, while weights classify representations. Fundamental weights provide a basis for labeling representations, and Dynkin labels give a compact way to specify which combinations appear. At this point, one naturally asks, how do weights actually classify representations? The key idea is that every irreducible representation has a highest weight, usually denoted by lambda. Dynkin labels are obtained by comparing this highest weight with the simple roots, alpha, through an inner product. The numbers, A, become the Dynkin labels. This gives a practical bridge between geometry and representation theory. Roots determine the structure of the algebra and its Dynkin diagram, while weights tell us which representation we are looking at. For example, in SO10, the Spinor representation 16 has a highest weight where only the fourth coefficient is active, giving the Dynkin label. This means that only the fourth Dynkin node is active. For SO10, the Lie algebra is D5. Its Dynkin diagram contains 5 nodes arranged in a characteristic shape with symmetric rabbit ears at the end. A Dynkin label such as A1, A2, A3, A4, A5 tells us which fundamental weights are activated. The crucial point for SO10 is that the last 2 nodes, 4 and 5, are special. They correspond to the Spinor representations. This simple geometric observation already explains why labels such as 00010 and 00001 repeatedly appear in SO10 discussions. Before diving into the geometric details of each representation, the table below provides a quick reference summary of the core SO10 patterns we will explore. These are not all possible SO10 representations, but they are the ones that appear most often in GUT discussions. Before moving to larger tensor numbers, we must address a natural question: why do GUT tables focus so heavily on the product 16 times 16? The reason comes from the core structure of quantum field theory. Lagrangians must be gauge invariant scalars. To build a mass term or a Yukawa interaction for fermions, we must couple 2 fermion fields together with a Higgs field. Since all known fermions of a single generation live inside the 16 representation, any interaction that gives them mass requires a specific combinations of fields, which structurally looks like this. To see which Higgs representations, H, can legally couple to our fermions, we look at what comes out of 16 times 16. This physical necessity is why the decomposition of this specific product is the heart of SO10 model building. The 10 representation. Dynkin label 10000. This corresponds to the 10-dimensional vector representation. One may think of it as a tensor TA with the index, A, running from 1 to 10. In many SO10 constructions, Higgs fields live in this representation. The 45 representation. Dynkin label 01000. This corresponds to the 45-dimensional adjoint representation. This can be written as a rank 2 antisymmetric tensor TAB, satisfying TAB equals minus TBA. To count the independent components, we choose 2 indices out of 10. This gives 45. This is the representation in which SO10 gauge bosons live. Mathematically, it arises naturally from the particle-antiparticle product 16 times 16 bar equals 1 plus 45 and so on, ensuring that gauge bosons can mediate interactions between fermions. The 120 representation. Dynkin label 00100. This corresponds to a rank 3 antisymmetric tensor TABC. Counting the independent components gives 120. This representation appears naturally when we decompose the product of two fermion generations. This means a Higgs field in the 120 representation can generate specific types of fermion masses. The 16 and 16 bar spinor representations. Dynkin labels 00010 and 00001. These are different from the previous examples because they are not ordinary tensor representations. These are spinor representations, fundamentally related to Clifford algebra constructions. In SO10, they become the famous 16 and conjugate 16 bar representations. One remarkable fact of SO10 guts is that an entire fermion generation, including the right-handed neutrino, fits beautifully into a single 16. The 126 representation. Dynkin label 00002. The representation 126 occurs in the decomposition of 16 times 16. Mathematically, it corresponds to a complex self-dual rank 5 antisymmetric tensor TABCD+. It frequently appears in SO10 physics because it plays an important role in gut symmetry breaking and Majorana mass constructions, such as the seesaw mechanism for neutrinos. Conclusion. The overall picture is that numbers such as 10, 16, 45, 120, and 126 are not isolated pieces of data. They are organized by the geometry of the D5 Dynkin diagram, tensor structures, spinor representations, and the general framework of representation theory. Once this pattern becomes visible, SO10 tables begin to look less like magic and more like a dictionary.